Something happened on October 29th that has left scientists around the world quietly unsettled. As 3-1, Atlas swept past its closest point to the Sun, observatories on multiple continents recorded behavior so far outside known cometary physics that even the most conservative researchers admit they don't know what to make of it. Before we go deeper, ask yourself something not as a believer or skeptic, but as an observer standing at the edge of the unknown. If an interstellar object behaved in ways that looked intentional, would you recognize it? Drop a yes or no in the comments, because the next few minutes may reshape whatever answer you choose. What happened during perihelion wasn't a single anomaly. It wasn't a glitch in instruments or a one-off spike in data. It was a cascade of events unfolding in real time, defying expectations with such precision that entire research teams are rechecking data logs frame by frame. This is why global interest has exploded. For the first time in years, astronomers are watching an object whose behavior does not fully align with established natural models. That alone doesn't prove anything extraordinary, but it does mean something is happening that demands attention. And the deeper we look, the stranger it becomes. At perihelion, comets usually roar to life. This is among the most predictable events in planetary science. Solar heat increases, surface ices vaporize, the coma expands dramatically, and brightness shoots upward. Thousands of observed comets have followed this exact pattern. 3I, Atlas did not. Instead of intensifying, its activity collapsed. Within mere hours, while bathed in the most intense radiation of its entire journey, its coma shrank. Its brightness dropped sharply, and outgassing nearly disappeared. At 0.7 AU, closer to the Sun than Earth's orbit, this makes little sense under current models. High radiation should cause maximum volatilization, not suppression. Researchers describe it as if the object shut down, a phrase being used cautiously and strictly to refer to the measured drop in activity, not to imply any artificial mechanism. But even that cautious wording adds to the mystery. Why would heating cause less activity? One hypothesis proposes unusual thermal layering. Another suggests unknown volatiles not yet characterized. Both remain possibilities, yet the timing was so precise that it has triggered debates far beyond typical cometary discussions. And as the data expanded, the anomalies only multiplied, leading many to quietly wonder whether this object behaves in ways we haven't seen from natural interstellar bodies before. Spectroscopic data from the perihelion window revealed something even more puzzling. When Dr. Robert Warwick and his colleagues compared 3I, Atlas's emissions against known molecular libraries, several features aligned with complex carbon and nitrogen-bearing compounds, but others did not match any catalog reference. These unidentified signatures don't prove anything exotic. They simply indicate that this object may contain materials not previously sampled in laboratory conditions. Interstellar objects often originate in environments far different from our solar system, meaning unfamiliar chemistry is not unexpected. However, it was the sudden appearance of new emission lines specifically during perihelion that grabbed researchers' attention. Why would certain compounds only manifest at that moment? Temperature-driven changes are one explanation. High-energy radiation breaking apart molecules or creating temporary intermediates another. But the unresolved wavelengths highlight that we are observing something not yet fully understood. The uncertainties are driving a surge of cautious excitement in the scientific community. This doesn't confirm new physics, and it doesn't imply anything artificial. What it does confirm is that 3I, Atlas, is chemically unlike the majority of objects we've studied up close. And in interstellar science, encountering the unfamiliar is the rule, not the exception. Yet in this case, the timing, intensity, and complexity are unlike anything recorded before. Then came the infrared thermal data, perhaps the most quietly shocking measurement so far. Instead of showing the typical patchwork of hot and cold zones expected on rough, uneven, multi-material comet surfaces, 3I Atlas appeared to maintain an almost uniform temperature across the observable region. That by itself is unusual but not impossible. A highly homogeneous composition, or unusual surface texture, could theoretically reduce temperature variation. However, spectroscopic results point toward diverse materials, not uniformity. This paradox has opened heated debates. Could rapid rotation smooth out thermal differences? Some comets do exhibit moderate thermal averaging due to rotation, but available measurements of 3I, Atlas's rotation rate, do not appear fast enough for a perfectly even distribution. Another possibility is internal convection gases moving through porous channels distributing heat. Not impossible, but not yet supported by direct evidence. What makes the uniformity especially provocative is its timing. It occurred precisely at the point of maximum solar heating, when irregular bodies typically show the most variation. Again, this does not confirm artificial heat regulation or engineered thermal control. Such claims would require extraordinary proof. But the unexpected stability is undeniably intriguing. It suggests we may be witnessing material properties or internal structures not previously encountered in standard comet models. But perhaps the most attention-grabbing observation was the abrupt albedo shift. In less than 8 hours, 3I, Atlas became significantly more reflective, even as its activity decreased. For natural objects, albedo changes usually require substantial resurfacing fresh ice exposure, dust deposition, chemical transformation. Yet each of those processes has consequences we should have observed. Fresh ice exposure, for instance, generally triggers increased outgassing, not a reduction. Dust deposition tends to darken objects, not brighten them. Ultraviolet-driven chemical reactions remain a candidate explanation, but the speed of the albedo increase is still faster than what is typically documented in other comets. None of this implies a controlled mechanism. The scientific community is careful to emphasize that unusual natural processes remain entirely plausible. But the combination reduced activity, uniform temperature, and rapid brightening has created a pattern that doesn't align neatly with familiar models. Researchers aren't alarmed, they're intrigued. Because whatever is happening here, it is showing us a behavior few expected to witness in real observational data. And for the first time, many are openly acknowledging a possibility rarely considered, that interstellar objects might exhibit physical behaviors shaped by formation environments far more complex and far less predictable than we've accounted for. As if the chemical, thermal, and brightness anomalies weren't enough, the magnetic field readings raise entirely new questions. During perihelion, NASA's Parker Solar Probe collected magnetometer data as 3I. Atlas moved through the inner heliosphere. What stood out wasn't the strength of the magnetic disturbance site, was the structure. The reading suggested a localized, patterned magnetic fluctuation rather than the diffuse irregular signatures usually produced by ionized gases interacting with the solar wind. That alone isn't unprecedented. Metallic inclusions or unusual conductive minerals could create magnetic irregularities. But the intriguing part was the rhythmic pulsing, evenly spaced oscillations repeating over several seconds. In natural objects, such patterns are extremely rare, especially in small bodies. Scientists are not claiming deliberate magnetic activity, far from it. Several hypotheses are being considered, ranging from thermoelectric processes to complex interactions between solar wind and highly conductive material. Still, the regularity of the pulses has become a focal point of debate because it simply doesn't resemble typical cometary responses. And this is where the mystery deepens. No single model explains all the anomalies together. Different models can explain parts of what we're seeing, but a unified natural explanation for every observation remains elusive, pushing researchers to examine an unusually wide set of possibilities. But perhaps the most dramatic and controversial event from the perihelion window was the trajectory deviation. Early calculations of 3I, Atlas's path accounted for gravitational influences, solar radiation pressure, and the non-gravitational forces produced by outgassing. Despite this, when the object exited perihelion, it was several hundred kilometers away from its projected position. For natural comets, such deviations are usually caused by jets of material erupting from the surface, acting like small thrusters. Yet telescopes monitoring 3I, ATLAS, from multiple angles detected no significant jets at the time of deviation. No plumes, no venting, nothing that would generate measurable thrust. That doesn't mean jets weren't present. They could have been too faint, too brief, or pointed in angles difficult to observe directly. But the missing visible activity complicates standard explanations. Researchers remain cautious. Small but continuous outgassing, asymmetric heating, or rotational dynamics could still contribute to unexplained drift. However, the absence of obvious drivers has led to expanding discussions private, not official, about what combination of natural forces could produce motion without clear accompanying signatures. No one is jumping to extraordinary conclusions, but no one is dismissing the anomaly either. And this is where the story begins to shift from unusual physics to something deeper, a pattern forming across multiple independent observations. When you stack each anomaly side by side, chemical irregularities, thermal uniformity, rapid albedo changes, magnetic oscillations, and trajectory deviation, you begin to see why scientists are struggling. Individually, each phenomenon could be explained by uncommon or poorly understood natural processes. Interstellar objects originate in environments far different from our solar system, so encountering unfamiliar behavior is not surprising. But the synchronization of these anomalies during perihelion is what has many researchers leaning forward in curiosity. The scientific process demands restraint. Extraordinary claims require extraordinary evidence, and so far, no measurement definitively proves anything beyond unusual behavior. But even within that caution, there is growing acknowledgement that 3I, ATLAS, is behaving differently than most interstellar visitors we've observed. Theories range from exotic but natural materials to complex internal structures forged in ancient planetary collisions. Some propose cryovolcanic vents that respond in nonlinear ways to solar heating. Others believe structural porosity could produce thermal and magnetic interactions we haven't modeled yet. This isn't evidence of artificial origin, it's evidence of insufficient data. Yet the excitement is real, because whatever explanation eventually emerges, it will likely expand our understanding of physics, chemistry, or planetary formation. And for scientists, that is the kind of mystery worth chasing. Still, the debate surrounding 3I, ATLAS, is beginning to drift into questions far larger than classical comet science. When an object from another star system behaves in ways that push against established models, researchers are forced to evaluate multiple frameworks at once. One line of thought considers the possibility that we're observing natural phenomena that simply don't occur in our solar system. Another considers whether 3I, ATLAS, could be an interstellar fragment from an environment richer in metals or more geologically complex than anything we've sampled. But the third line, the one whispered more quietly, is the possibility of artificial processes. Not because the data proves it, but because the combination of anomalies doesn't comfortably fit any known natural chain of events. This line of speculation is handled cautiously, strictly as a hypothetical. Some researchers propose it might be an ancient probe, possibly damaged and functioning in unpredictable ways. Others counter that no measurement thus far provides definitive evidence of engineering or technology. The debate remains balanced, one side urging restraint, the other urging exploration. What makes this moment extraordinary isn't that we might be seeing technology, it's that the data is ambiguous enough to make the question worth asking at all. And that alone marks this object as one of the most intriguing interstellar visitors ever detected. What makes the situation even more compelling is what comes next. As 3I, ATLAS, moves away from the Sun and into cooler regions of the solar system, scientists expect entirely new behaviors to emerge. If it is a natural comet, activity should slowly decline as temperature drops. If its anomalies were caused by heating, they may stabilize. But if some of the unexplained behaviors persist or intensify, then the mystery deepens considerably. Will the albedo continue to change? Will magnetic patterns reappear? Will its trajectory deviate further from predictions? No one knows, and that uncertainty is rare. Typically, once comets pass perihelion, behavior becomes easier to model. But here, researchers are preparing for the possibility that 3I ATLAS may continue surprising us. The coming months may determine whether this object becomes a historical curiosity or a profound turning point. Either way, scientists agree on one point. Distance reduces opportunity. The farther 3I ATLAS travels, the harder it becomes to study. And right now, it is accelerating outward at tens of kilometers per second. Time and not data is the greatest enemy. If answers exist, they are drifting away from us every hour. As 3 Atlas drifted farther from the sun, telescopes expected its activity to stabilize into a predictable decline. But instead, researchers noticed something far stranger. The object began showing intermittent brightening spikes brief, surges lasting only minutes before fading again. These shifts were small, subtle, and easy to miss, yet consistent across multiple observatories. Natural comet outbursts can happen, but they're usually violent and sustained, triggered by jets of gas erupting from subsurface pockets. What Atlas display looked almost measured days if something inside it released energy in short, controlled bursts. Some astronomers argue these could be microfractures venting trapped materials, the kind of behavior we simply haven't recorded before in an interstellar visitor. Others warn against overinterpreting the data. Faint objects are notoriously difficult to analyze near the limits of our instruments, and yet the timing of these pulses lining up across different wavelengths hints that there's more happening beneath Atlas's surface than our current models can explain. Whatever the mechanism is natural or notice inconsistent with the smooth decline expected after perihelion, something is changing inside this object as it moves outward. And the deeper scientists look, the more questions emerge. This uncertainty has forced mission planners worldwide into heated debate. Space agencies know that the ideal moment to study an interstellar object is no while it's still close enough for a spacecraft to catch up, but there is no agreement on what kind of mission would be most viable. A fast flyby could capture high-resolution imagery and spectroscopy, similar to what we did with Oumuamua and Borisov. A rendezvous mission would be exponentially more valuable, but far more difficult, demanding precise navigation, advanced propulsion, and political approval. Nations like China, Japan, India, and Europe have shown public curiosity, yet none have formally committed to a launch window. The hesitation isn't because the object lacks importance, it's because the scientific community is divided. Some insist Atlas is simply behaving like a type of comet we've never seen before, one that challenges our assumptions but remains natural. Others argue that the object's combination of anomalies, its inconsistent brightening, its unusual spectroscopic features, its unexpected stability, suggests a chance to discover something fundamentally new about the building blocks of other star systems. And that possibility alone makes the lack of action increasingly frustrating, because here's the reality. Interstellar samples are priceless. Every fragment, every molecule inside 3 Atlas represents chemistry untouched by the Sun, Earth, or anything from our solar neighborhood. Even without exotic behavior, even without speculation, an object like this is already a once-in-a-generation scientific treasure. Studying it up close could rewrite our understanding of how planets, asteroids, and comets form in distant systems. But the clock is ticking. Atlas is accelerating outward at tens of thousands of kilometers per hour. For every day agencies debate funding, trajectory, and mission design, the object slips farther away, making any intercept mission longer, harder, and more expensive. The tragedy is that we can reach it. We have the technology. What we lack is consensus and courage. Humanity has waited centuries for a chance like this, a chance to examine an untouched traveler from another star. Letting it fade into the darkness without even trying would be one of the greatest scientific opportunities we've ever allowed to vanish. Yet not everyone agrees a mission is worth the risk. Some researchers argue that the anomalies we've observed could simply be the result of limitations in our instruments' data distortions, observational blind spots, or processes we've never modeled properly because we've only studied comets from our own solar system. Interstellar objects could simply behave differently. Their internal structures, volatile mixes, and thermal responses might follow rules we're just beginning to glimpse. If that's true, then what we're seeing isn't artificial, it's a new chapter in cometary science. Others counter that the pattern of unexpected behavior shutdown near perihelion, uniform temperatures, sudden reflectivity changes, subtle directional deviations demands deeper investigation no matter the interpretation. After all, discovering a new kind of natural physics is just as revolutionary as discovering alien technology. Both outcomes expand humanity's understanding of the universe, and both require the same first step, getting closer. So now we stand at a crossroads. 3 Atlas is already slipping beyond the orbit of Mars, sailing into the deeper cold where sunlight fades and its mysteries retreat into shadow. We may never observe another object like this, again not in our lifetimes, and perhaps not for centuries. Whether Atlas is an unusual comet, a fragment of an ancient planetary system, or something entirely different, its presence challenges us. Do we allow fear of embarrassment, political hesitation, and institutional caution to dictate our response? Or do we reach for the unknown the way our ancestors once reached across oceans and deserts, driven by nothing but curiosity and the desire to understand? The universe rarely knocks twice. Atlas may be the question quiet, distant, and rapidly fading. The real mystery is whether humanity will answer before the darkness closes around it forever.